Hello, myself Onik here, and I'm here with my project titled Architectural Style Classification using Deep Learning and Transfer Learning. I have completed this project, and also my teammate Madhurjo has assisted a bit. The goal of the project is to classify building image into 25 architectural style categories using transfer learning. We used two public architectural image datasets, merged them, cleaned them, trained EfficientNet B0, fine-tuned it, and compared it with a logistic regression baseline. Architectural style classification is challenging because many styles share similar visual features such as columns, arcs, windows, roof shapes, facade symmetry, and ornamentations. For example, Greek Revival, Palladian, Colonial, and Georgian style can look visually similar, so this is not a simple object detection task. It is a fine-grained image classification problem. In the literature review, we found that earlier architectural classification methods used handcrafted visual features and classical machine learning. Later, CNN-based deep learning and transfer learning became more effective because they can learn spatial and symmetric visual features directly from the image. Based on that, we used EfficientNet B0 with ImageNet pre-trained weights. And here in this methodology part, this is the complete workflow of our project. First, we downloaded the two datasets, then we merged them, cleaned labels, checked corrupted image, removed duplicate images, performed EDA, exploratory data analysis, split the dataset into train, validation, and test sets, applied data augmentation and class weights, initialized EfficientNet B0, trained it for 10 epochs, fine-tuned it with a lower learning rate, and finally evaluated the results.
The pre-processing was done properly because we did not directly train on the raw downloaded data. First, we merged two public datasets into one unified dataset. Then we cleaned the labels, checked for corrupted images, and removed exact duplicate images to reduce leakage and bias. After that, we used a stratified train validation test split so that all 25 classes were represented in each split. For model input, images were decoded, resized by 20, 224 by 224 pixels, best and prefaced using TensorFlow datasets. We also used class weights to handle imbalance and data augmentation to improve generalization.
For pre-processing, we merged two datasets. First dataset had 9588 image and the second one had 15432 image. After checking the corrupted images, we found 0 corrupted files. Then we moved exact duplicate images using image hashing. After removing 15,162 duplicate image, the final cleaned dataset contained 9,858 unique images across 25 architectural classes. We also performed EDA using class distribution and sample image visualization. The class distribution showed imbalance, so we later used class weights during training. And here's the bar chart we can see, the one we got after performing EDA. And here, by observing train, validation, and test split bar chart, the cleaned dataset was divided using stratified train validation test splitting so that all 25 classes were represented in each split. The final split contained 6,900 training image, 1479 validation image, and 1479 testing image. For model input, images were decoded into RGB format, resized into 224 by 224 pixels converted into float 32 patched with patch size 32 and prefetched for efficient GPU training. For the main model, we used EfficientNet B0 with ImageNet pre-trained weights. We removed the original top classification layer and added our own classification head with global average pooling, dropout and dense softmax layer with 25 outputs neurons. Each output neuron represents one architectural style class. And here the number of classes and the name as well are shown. Here the data augmentation pipeline is created successfully. The initial EfficientNet model was trained for 10 epochs using learning rate 1 E-4. We used data augmentation, class weights, checkpoint saving, and model saving. After that, we fine-tuned the model by unfreezing the 40 layers of EfficientNet B0 and reduced the learning rate from 1E4 to 1E5. This lower learning rate allowed the model to adjust the predetermined features more carefully. Here the fine-tuning curves shows that the validation accuracy increased and loss decreased, which means the model continued learning after fine-tuning. We also ran 5 epochs following the same procedure later on. We compared three models: Logistic Regression, Baseline, Random Forest, EfficientNet B0, trained for 10 epochs, and fine-tuned EfficientNet B0. The Logistic Regression baseline achieved only 13.90% accuracy because flattened pixel features cannot capture architectural patterns properly. The 10 epochs EfficientNet B0 achieved 53.58% accuracy. After fine-tuning, the final EfficientNet B0 model achieved the best result with 57.54% test accuracy, 56.62% macro F1 score, and 56.62% weighted F1 score. The other three models we used are KNN, ResNet, and Vision Transformer. Here, the fine-tuned confusion matrix shows that the model correctly classified many images, but some confusion still remained. This is expected because architectural styles are visually similar. For example, Greek Revival and Palladian may both contain classical columns and symmetrical facades. Colonial and Georgian may look also similar because of the balanced facades and rectangular windows. Single image prediction can also be wrong due to lighting, camera angle, occlusion, background clutter, or unclear facade visibility. As we have merged three datasets total, so we skipped Wikichurch dataset download here. Here it's shown that the unified dataset is created. And here we can see we found zero corrupted image in our datasets. Kinda it's almost pretty much perfect dataset. which has 25 classes. Here we run hashing to remove all the duplicate images from our dataset. And here we can see the logistic regression confusion matrix that we got from our dataset. And all other confusion metrics like random forest, KNN, ResNet 50, EfficientNet B0 and vision transformer are here as well, serially.
Even though the model learned useful patterns, some predictions can still be wrong because architectural style classification is a fine-grained task. If a building image is ambiguous or belongs to a visually similar style, the model may predict the closest available class incorrectly.
We also implemented a lightweight logistic regression baseline using flattened 24 by 24 RGB image features. It achieved 13.90% accuracy, which was much lower than EfficientNet B0. This shows that traditional pixel-based machine learning is not enough for this task, and deep transfer learning is more suitable for it.
From the comparison, the best performing model in this project is the fine-tuned EfficientNet B0. The logistic regression baseline achieved only 13.90% accuracy and the initial EfficientNet B0 model achieved 53.48% accuracy. After fine-tuning with a lower learning rate, EfficientNet B0 improved to 57.54% test accuracy with a weighted F1 score of 56.62%. So we selected fine-tuned EfficientNet B0 as the final model.
And here in the paper, we added the methodology and the architectural style classification pipeline, class distribution after dataset merging, duplicate removal, and sample images from 25 architectural style classes, train, validation, and test split image, final model performance comparison, fine-tuning accuracy and loss curves of EfficientNet B0, confusion matrix of the fine-tuned EfficientNet B0 model, and also logistic regression light confusion matrix with numbers, and performance matrix comparison table. And finally, the conclusion and references. In conclusion, this project successfully built a complete architectural style classification pipeline. We completed dataset download, merging, preprocessing, duplicate removal, EDA, stratified splitting, data feeding, augmentation, class weighting, efficient net B0 training, checkpoint saving, fine tuning, evaluation, confusion matrix analysis, logistic regression baseline, and final comparison. The best model was fine-tuned efficient net B0 with 57.54 test accuracy. The result can be improved in the future by using a larger balanced dataset, stronger models, longer training, and more domain-specific image cleaning. For future work, the performance can be improved by using a larger, more balanced dataset, training more epochs, using stronger architectures, and applying a better domain-specific image cleaning. Additionally, techniques such as attention mechanism or explainable AI methods like GradCam could also help us understand which architectural features the model is focusing on. And here I have added the references I used while going through this whole project. It is Anik Rahman signing out. Thank you.